Imagine trying to test gravity not where it is strong and obvious, but where it is barely whispering, at accelerations so faint that a grain of dust would hardly notice. That is the stage for the current debate. Two stars, very far apart yet still bound to one another, drift through the galaxy together. They are called a wide binary because they tug so gently. They let us probe gravity in the regime where standard theories, Newton's equations and Einstein's general relativity, have had the least direct laboratory-like scrutiny. Some recent analyses of these star pairs report a surprise. When the tug becomes extraordinarily small, around 1/10 of a nanometer per second squared, the attraction between stars appears 30 to 40% stronger than standard gravity would predict. At higher accelerations, everything looks normal again. If that pattern holds up, it resembles what certain modified gravity ideas, especially Mond and its equal formulation, have been anticipating for decades. It would not overthrow Einstein's theory, but suggests that in the quietest corners of the cosmos, the familiar rules bend ever so slightly. That is the headline. The controversy is about what justifies believing it. To make sense of the back and forth, it helps to think in threes. Three interlocking questions that must rise or fall together. The first question is about method. Are the measurements and data hygiene good enough? The second is about signal. Is there truly an anomaly at ultra-low accelerations? The third is about explanation. If the anomaly is real, does a Mond-like theory actually account for it better than standard gravity? Let's start with the method. Wide binaries are deceptively tricky. They can be contaminated by hidden third stars. They can be pairs that only appear bound because they're just passing one another. Or they might even be members of loose-moving groups that imitate a weak gravitational tug. So analysts really have to build clean catalogs, measure the three-dimensional motions of both stars, correct for perspective effects, and stress test their selections. Now, proponents of the anomaly argue that when you do all this with care, the data reveal a consistent excess in the slowest dances. But critics counter that once you model hidden triples and other systematics comprehensively, the excess fades into consistency with Newton and Einstein. In plain terms, one side says, good hygiene reveals a real effect, while the other says, better hygiene removes it. Now, onto the signal. Suppose one accepts that the curation is excellent. Then the low acceleration strengthening becomes the centerpiece. The pattern matters. There's nothing anomalous at higher accelerations, and then a smooth statistical rise in apparent gravity as you cross into the ultra-low regime. That is exactly the region where Mond-like theories predict a departure. Conversely, if the careful reanalyses show no such transition, or if the effect depends sensitively on a small subset of stars or a particular set of cuts, confidence erodes. So the argument becomes, if a robust signal exists, it should survive reasonable changes in how the sample is cleaned and how the motions are modeled. Finally, the explanation. Modified gravity models don't just predict more gravity, they actually make structured predictions. Equal, for example, anticipates a characteristic boost, order unity, not just a small tweak near the critical acceleration scale, and it predicts that the environment matters. The galaxy's own gravitational field can imprint a directional bias on the motion of the binary, an external field effect. That gives the debate something better than a simple yes or no, a signature. So, if a future cleaner catalog reveals not only an overall excess at very low acceleration but also a directional pattern, aligned with the local galactic field, the case for modified gravity advances from intriguing to compelling. If instead high-quality data find no such pattern, the modified gravity interpretation weakens, even if occasional hints of excess remain in noisier subsets. So, those three questions, method, signal, explanation, do not live in isolation. They actually form a triangle of implications. If the method is truly clean, then a genuine low acceleration signal becomes much harder to just dismiss as some kind of artifact. If a robust signal is really there, a theory has to be identified that explains not just its existence, but also its detailed shape. And if a modified gravity theory turns out to be the right explanation, then improved data should just keep finding the signal. But, if you turn that triangle around, you get the skeptic's position. If no signal survives the most careful analyses, that retroactively indicts earlier methods as insufficient. and it removes the need to invoke new physics. So in other words, each corner of the triangle carries the other two with it. There's actually a second triangle at play here, and this one's about process rather than physics. First, the community needs a uniformly vetted, shared catalog of wide binaries. The same sky, the same stars, the same agreed-upon checks for hidden triples and imposters. Second, it needs pre-registered blind analyses on that catalog, so that the choices about cuts and models are declared in advance rather than tuned after the fact. Third, it needs convergence across methods and instruments. Three-dimensional velocities from space astrometry must match what two-dimensional sky-projected methods and independent radial velocity campaigns find. When those three steps reinforce one another, the field can finally escape the current cycle of my pipeline versus your pipeline. But when anyone is missing, the cycle just tends to spin in place. Disagreement about the catalog undermines pre-registration. Lack of pre-registration undermines convergence, and lack of convergence undermines the incentive to share and refine a common catalog. There is even a third triangle, this time across cosmic scales. On galaxy scales, Mond-like relations have long shown an uncanny knack for organizing rotation curve data with few free parameters. On the smallest scales, within the solar system, and in precision laboratory tests, Einstein's theory works exquisitely well. Wide binaries live in between. For a single theory to be satisfactory, it must harmonize all three scales. If galaxies and binaries both point to the same kind of low acceleration departure while local tests remain unviolated, one can imagine a graceful bending of the rules in just the right regime. If, on the other hand, binaries fall into line with standard gravity once the data are impeccable, then the harmony breaks, and the modified gravity score loses a crucial section. With these three triangles in mind, it becomes easier to understand why both excitement and caution are justified. The excitement comes from a crisp, testable narrative. At a very specific acceleration scale, the universe might be telling us that gravity changes character. There might be a faint fingerprint, an environmental directionality, betraying the mechanism. The caution comes from the reality that such a delicate signal can be mimicked by mundane effects. A small fraction of undetected triple systems, subtle biases in the way distances and motions are measured, or how candidate pairs are selected, can add up to exactly the sort of pattern that tempts us toward new physics. What, then, would constitute a decisive next act? Assemble a community catalog that everyone agrees is clean to the same standard. Commit to a pre-registered analysis plan before looking at the answer. Pursue the external field signature specifically. Do the residuals point, statistically, along the galaxy's own pull, and ensure that independent teams, using different tools and independent velocity measurements, find the same result. If all of those steps line up and the signal persists with the predicted directionality, it will be strong evidence that gravity's familiar script bends in the quietest reaches of space. If they do not, the anomaly story will recede, and the status quo will stand strengthened. Einstein bends, not breaks, is a fair summary of the most interesting possibility on the table, but whether that line belongs in the textbook will be decided not by one paper or one pipeline, but by whether method, signal, and explanation lock together, and whether the community's process achieves the same alignment.